Welcome to the first Math Club talk of 2026. Today we have Ramdas Singh. He is a B.Math second year student and will be giving a talk on Sobolev spaces. He is mainly interested in functional analysis. Over to you, Ramdas.
Thank you, Yash. So today's topic is weak derivatives and Sobolev spaces. We'll be extending the idea of derivatives to not really differentiable functions. So to start off, if I have two functions f and psi, which are very differentiable, integration by parts tells me that the integral of this is exactly equal to f psi evaluated at a and b and minus f dash and psi from a. This is what integral parts tell me. If I also require psi to vanish to be clamped with the endpoints, then this term goes to 0. Exactly. Instead, we have the condition that the inner product of f and psi dash must be minus of f dash and psi. So this is one condition of one property of C1 functions, where if I have a clamped function and I take the integral by parts, I get this. This identity is exactly what will redefine our derivative in terms of weak derivatives. So to extend this formally, let AB be a compact integral in R, and we denote this space C01 AB to be all those C1 functions which are clamped with the endpoints. Exactly the condition of the code. This is the space of test functions. Correct? Now for any let's say any f in C1, we already showed that condition. So instead, for any f in square integrated functions, s squared a to b, let's say f is weakly differentiable if this is satisfied by some g. So f is weakly differentiable if there is another function g which satisfies this identity. It may seem a little out of the blue, but there is a reason why we have this space and this space, and this is exactly the part of the next topic where we require a lemma to properly formulate this. And the lemma, it says that the space of test functions is dense in the space of square integrated functions. And moreover, if g and h are two square integrated functions, let's say a to b, such that the integral of g with this psi and the integral of a to b, the integral of h with psi, this is equal for all test functions. Then g and h must be equal, almost everywhere. Correct? So to show a proof of this, again, I'll be working mostly proof sketches, not full-blown proofs. To show the first part, density, one can show that the space of test functions is dense in the space of continuously differentiable functions, which is again dense in continuous functions, which is dense in S squared, which again implies density this way. That's why you show the first part. For the second part, it follows from the first part. Since C01 is since C01 is dense in S squared and G is in S squared, this is equivalent to showing that if f psi of AB is equal to 0 for all C, then f must be 0. identity, almost everything. Because I can take f to be g minus h and the identity holds. So here I can take a sequence of test functions in C01 pt such that the test functions they converge to f, since C01 is dense in L square and f is L square. Then I simply have integration of f square as integration of f cn. I can take a limit outside since this is a bounded linear function. And this, we know it's 0 for all test functions, so this is limit as n tends to infinity of 0, which is again 0. And if the integral of any non-negative function is 0, then that function must be identical to 0, almost everything. So that's the lemma proof. And using this, we define this. So let's look at definition. F in S square is V differentiable if this identity is satisfied by some square integral function for all test functions. And using that lemma, one can show that if there exists a g, this g must be unique. Since I'll write a small lemma. Such a g is unique. Since the proof again is very simple. If I have, so in this case, g is from the weak derivative of f. So if I have two weak derivatives of f, let's say g1 and g2. Then the identity implies that g1 times c is equal to f c dash is equal to g2 times c, and this is for all c. But since this is equal to this for all test functions, that lemma tells me that g1 must be identical to g2 almost everywhere. So this is unique. And from here we can define our new space, which is called the Sobolev space of first order, which is defined as all those square integral functions on the AB such that f is Vg differentiable. And you can check this is the linear space. To show that it makes sense in some way, we look at a few examples. So let's look at an example of the function absolute value of t on minus 1 to 1. So of course, I think many of us have thought of this like this way. That is function. We know intuitively the function must have a derivative of something like this. -1 here and 1 here. And here we would have maybe take it to be 0. But it's not differentiable here. We show it's weakly differentiable. And this sign of t is exactly the weak derivative of absolute value of t. So to show this, we have to show that f t dash is satisfied by this. Let's say f dash. So another thing, for weak derivatives also we write f dash to denote the weak derivative of f. So it is better to show that the sign of t satisfies this identity. So if I expand this, -1 to 1, I'll just write. So this is the left hand side, which expanding mod of t in terms of -1 to 0 and 0 to 1, this becomes this. which if I now apply integration by parts in the individual terms, this is p psi t from -1 to 0 minus -1 to 0 of psi t dt, and this term becomes plus minus p psi t. This is from 0 to 1. The last term is this. Yeah. So if I have this, then this evaluated at 0 cancel out with this one evaluated at 0, and since psi is a test function, it must minus at the end. Psi minus 1 is 0, psi of 1 is 0. So at minus 1 is this term 0, at 1 this one is 0. So we have this term plus that term, which I can rewrite it as -1 to 1 sine of t sine t dt, and taking negative sign here and here gives me exactly sine t. So this shows that the sine of t is the derivative of mod t. As a few non-examples of weakly differential functions, which I will explain later why they are non-examples. Non-examples. One is sine of t. Sine of t on -1 to 1. This is not weakly differentiable, as we will see later. But basically, it boils down to the fact that if it had a weak derivative and if you integrated it, you wouldn't get sine of t back. We will show the fundamental theorem of calculus later. Another non-example is root of t on 0 to 1. Since we require that the weak derivative must be square integral, a little bit definition. We require f prime to be in n square, but the integral of root of t, the weak derivative, which is 1 by root t, sorry, this square dt from 0 to 1, it's not less than infinity, so it's not square integral. So this is not a weak derivative. Moving on, we now will completely formulate the fundamental theorem of calculus, for which we need a lot of lemma corollaries. But basically, if I look at the classical setting, if I look at the classical setting, then I recall that we had the integral operator, which on a function j of t was defined as the integration from a to t of f, let's say fst, which is also the inner product of f with the identity function, the integrated function of a to t, and this was for all t in the interval, and for all square integral functions on a t. And this function gf was also continuous. It maps square integral functions to continuous functions. We also had the differentiation operator, which was a left inverse of g. What I mean by that is the dg of f of t was d by dt of this a by t f and ds, and this was exactly equal to f of t by the fundamental theorem of calculus. So j is a right inverse to d. We wish to extend this idea to a new notion of Lebesgue integrals and weakly differentiable functions, and we show its identity still holds in the new notions. To show this, we need to define first define the integration operator, which is very clear. So it's defined exactly as that, but we need a few results to make it nicer. Basically, lemma, this operator j from L squared AB to continuous function is continuous, is bounded, and one has that the function it maps onto is bounded as such. And moreover, GF is weakly differentiable with GF prime to be exactly F. To show a proof of this, so we know to land and continuous functions, we show the boundedness. Basically, for a function f, for the square root function s square root, we have this set of inequalities where gf of t is written down exactly as this. This is bounded by if I can take actual infinite bounds like that. And I can extend this to b since it is a non-negative function, so the inequality still holds. And this I can write it down as the inner product of mod f with the identity unity function everywhere. And again, by the Cauchy-Schwarz inequality, this is f2, this is 2, and this is exactly equal to root of b minus a. This is the norm of the ideal function times f2. So the integration operator is bounded, so it's continuous. Using the first part, I can show the second part, which I guess I can show you. So we need to show that JF with phi prime is minus of f with psi for all test functions. So if I take the linear functional from L squared AB to R and define it as T of f is defined as JF C dash plus G of C. Here we take C to fixed. Let's say this is TC. Correct? Now, since this is a composition of addition and inner product and stuff like that, T and it has involves J and J is continuous, it is bounded. That implies T is also continuous and bounded. In particular, if f is a C1 function, C1 is an S square. If f is a C1 function, then we know that Tc of f is equal to 0 because we can use the f is C1, it's classically differentiable. We can use integration of parts and these terms cancel out by the first identity. And since C1 is dense in S square, it is dense in S square, that means any f function, any quint function, I can take a sequence of C1 functions that converges to my desired f. And since J is continuous, I can extend the limit outside, and that will exactly give me that T is identically 0 for all functions. Since for any SL function, I can take a sequence of C1 functions and merge to it. Since this TC is continuous, if I apply it on the sequence, T of fn is 0, that means T of f must also be 0. So T is identically 0. Which implies that again, J of C dash equal to minus f C dash. Since C and C cannot matter, this goes for all C. So we have shown that f is exactly the B greater of J of f. From here, we had another identity in the classical setting, where if a function had a derivative 0 everywhere, it had to be constant. To show that, we need a little bit of heavy result, which says that L squared orthogonally decomposes as it can be written down as the derivative of a test function. This is the closure of it with respect to the norm plus the span of the identity function. So basically, any square function can be written down as the limit of derivatives of test functions plus a constant. So to show a proof of this, let's denote this space by f and this space by g. So we need to basically show that f closure is contained in g perpendicular and g perpendicular is contained in f closure. One of these directions is easy because one is perpendicular to f. Since integration of a to b c dash of x to ds, this is the inner product. One with let's say the derivative of a test function, and this is equal to c of b by c of a. But since it is clamped to endpoints, this is exactly 0. Or basically, we have f is contained in the perpendicular b. Since the orthogonal complement of g is a closed subspace, we must also have the closure of f is also contained in g. So that's one direction. The next direction is little tedious. So we will look at the orthogonal projection onto g perpendicular of f for some f in S square. This is identity minus the orthogonal projection of f onto g, which if I write it down, it's f minus f with the unit vector, which is 1 by root b minus a times the unit vector, which is converted to b minus a here. So this is the orthogonal projection of a function f, which is from f to s square. This is the orthogonal projection of f onto the orthogonal complement of g. If I apply the integration operator on it, j p g perpendicular f, we get g of f minus, this is a scalar I found out, j of 1. Correct? And so this is this j from a to some b. So if I for any f, for any f in s square dv, note that g is perpendicular of f evaluated at a is 0 by definition, since g takes an integral starting at a. Correct? We show that the other endpoint, which is j p perpendicular f of b. This I can write it as jf of b minus f with identity b minus a, and this if I write it down as an integral is basically a to b 1 ds. this is again A to B f is this, and this b minus a cancel out with this b minus a. So this is minus of f with 1. But this inner product is exactly this, and as a negative sign, so it is basically 0. So g of this projection is clamped in points. So what that means is so we have shown that J, the orthogonal projection of f is contained in C01A. It's even because I mean, let's say for any f in this continuous function. For the classical setting, this makes sense that the integration would land in C01. So in general, for any f square here, I can take a sequence of continuous functions converging to this f. We take fn and we will do one contained in C of A such that fn converges to f. And since the orthogonal projection is a continuous ring mapping, this implies that Pg this of fn goes to Pg perpendicular of f. And since this is bounded, so that means P, G, and Fn, it must land in F. And since we have taken okay, yeah. So this is the orthogonal projection. The range of this orthogonal projection must exactly be this G perpendicular, correct? So if I take a f in L square and I apply the orthogonal projection on it, it lands in G this. And since it lands in G this PG perpendicular of Fn must also land in F, which implies that G perpendicular is contained in F, which is contained in the closure of F. So we have shown that G perpendicular is in F closure. So that completes the proof. So basically, I can write down any function as the limit of sequence of derivatives of test function plus the constant. Little heavy to say, but yeah. The corollary of this is the fact that if f dash is identically 0 almost everywhere on AB, this is a weak derivative, then f is constant almost everywhere. So by definition, f is perpendicular to capital F, where capital F, okay, I just did it. So defined as derivative of test functions such that given C01 2. This is by definition, since we have f p dash equal to 0. So this is f in here, which implies that f is perpendicular to f this, but f closure was shown to be the orthogonal complement of identity. And since the orthogonal complement is clear, it must imply that f is contained in the span of identity, or f itself is a constant c times identity, and that is true. From here, we can characterize H1 properly. And this is a good theorem. It basically says that the space of weakly differentiable functions, it embeds into a CAD. I shouldn't write subset. It's basically any weakly differentiable function is almost everywhere equal to a continuous function. That is, if it is so this shows that if sine of t, I can't really make it equivalent almost everywhere to a continuous function. However, this mod t was a continuous function, so it could land in H1. But this is not even in C, so it has no hope of landing in H1. That's the idea here. And this is almost everywhere equivalence. And more precisely, a function is weakly differentiable if and only if f is equal to j plus c1 for some coordinate function s square, g in s square, and some real number. If only if f is this representation and such a representation is unique. Again, to show proof of this, if I have this representation, then f is weakly differentiable, since I have f prime equal to jg prime plus c1 prime, but this is basically 0, and we show that j is a right number to this prime, so this implies g. So f is weakly differentiable with g. So that's the reverse direction prime. For the converse direction, let's watch that. For the converse direction, which is the forward down, let f be weakly differentiable. H1 3. Let's set g to be the weak derivative of f and h to be the integration of g. Then if I take f minus h, if I prime this, I must have f prime and s prime, where f prime was said to be g and the prime of h, which is jg, is basically g, which is equal to 0. That means this f minus h function has a derivative of 0, which implies that f minus h, since it has a derivative 0, it must be constant and almost everywhere. So this is equal to C identity for some C in R, which if I take h to the right hand side, f is basically jg plus c1. Correct? More precisely, g was taken to be f prime. To show this representation is unique, we have if I evaluate this at A, f of A is equal to j dash of A plus c1 of A. But this is 0, it's an integration, integration from a to a 0. And this is 0 plus, this is the identity, so it's just 1 and c. This implies that c is equal to f of a. So the representation is in fact j f prime plus f of a into identity. So to show uniqueness, let j1, j2, let this will have a unique. Let f be written as jg1 plus c1 identity and written as jg2 plus c2 identity. Okay. If I subtract this from here and if I take the differentiation, I get j1 minus j2 this whole the prime plus c1 minus c2 whole under prime. This is 0 and this is the integral operator, so the differentiation is just this itself. And this, since this is f minus f basically, this differentiation must be 0, which implies that g1 equals g1 equals g2, which then implies that c1 equals c2. So this differentiation is unique, and that is this proof. And to finally, as a corollary is the fundamental theorem of calculus, where I like this one. The corollary is the FTC, which is basically for any weakly differentiable function and any compact subinterval of AB, one has f of b minus f of c as the integral of c to d of this f prime of x dx. Proof, we use the previous theorem to write f as f of t uniquely as j f of t plus f of t. Correct? So the difference side is basically f of b minus f of t. F of t is cancelled out, which is basically g f of d minus j f of c. So again, this is integrals, this is a to d, this is b to c, and I can subtract I can combine the one table to get c to d f prime of okay, this is j f prime, correct? Yeah, and this f prime is 0, and that completes the fundamental theorem of calculus. So moving on from this extension into a new notion of field derivative, we want to examine somewhat the structure of H1. So here I will tone down the proofs a bit. I think this is the last proof case section. So now I want to talk about specifically H1. On H1 we can define the inner product of two weakly differential functions. And I write H1 here. I can define it as this fg L squared plus f prime g prime L squared, which is integration a to b fg plus f prime g prime. And you can take this as a valid inner product because it's the sum of two inner products. And this induces the norm of a weakly differential function h1 as root of f squared plus f prime squared and square root. And the theorem is this space h1 dv equipped with this inner product is a Hilbert space. it should show small proof. If I take a sequence of f converging from f and h1 if we take a Cauchy sequence, by this law and these two laws, the same sequence must be Cauchy in L squared, and the primes of the sequence must also be Cauchy in L squared. And since we know L squared is complete, there exist limits of these functions, and I can show that the limit of this is exactly the weak derivative of this, and so I can use that limit to show that my Cauchy sequence in here converges to that function. So I'll open the proof here. It's basically I get the Cauchy sequence from here to here. That's the idea. And there's also another theorem where we have several operators. Again, I don't want to dive too much into it here, but basically, theorem. The following are bounded linear operators. And these ones are the differentiation from h1 AB, which lands in L squared, mapping f to its weak derivative. This is a bounded linear operator. The second one, the inclusion of h1 AB, where a function is mapped to itself in L squared. This is also a bounded operator. And finally, the inclusion of h1 AB into continuous functions, which we showed earlier. This is also a bounded linear operator. Again, I won't show proof of this, but this is some interesting operators to look into. If I want to look into higher spaces, one way to higher spaces, definition for n greater than equal to 2, we define h n a b as all those weakly differentiable functions h1 ab whose weak derivative lands in the n minus 1 order Sobolev space. And this is how you define the higher order Sobolev spaces. Basically, f prime must land in h n minus 1, f double prime land in h n minus 2, etc. So this is a recursive definition. And on here, the inner product of hn is defined as a to b f3 f prime d9 nth weak derivative, nth weak derivative. And this is a binary inner product because it's the sum of inner products on the spaces. And this induces the law this induces the law from defined as hn squared defined as from k equals 0 to n kth derivative in L squared. And properties h and ab equal with this inner product is Hilbert. The same proof works here, same argument. And a second part of this is that the C and A, the functions with nth derivative continuous, is Hn dense in Hn. Okay, so far we have talked about this abstractly. To show a proper application of this,
The key runs from 1 to n.
here from 0 to n. This is the f.
Oh, in prime.
Yeah, yeah. Yeah, okay. To show some applications, one is the Poincaré inequality, which says that for the space of so we'll shift from C01 to H01. We call this a space of test function now, which is basically all those BG differential functions which are clamped at endpoints. Same thing. For this space, there exists a constant c greater than 0 such that the L squared norm of this is bounded by c the u prime L squared for all u in the space. Correct. Proof since u is an H01 and u of A is 0, by the fundamental theorem of calculus, u of t can be written down exactly as a of t u prime s ds. If I apply Cauchy's formula on this integral, I can take this inside u prime s ds, and I can apply formulas on this specific space, which is basically this specific integral. So this becomes this is the inner product of u prime with id. So this, okay. Instead, this is a better way actually. But if point here into this by square, this is square. Then I can apply control here, and then I can get t minus a, an integral of at u prime s ds. If it is integral from a to b, and take this t minus a from b minus a, then b minus a u prime s square. If I integrate over t on here, so integrating over t, integrating gives me that one is u l squared, and let me equal to integrating this is actually multiplied by another b minus a. So this becomes b minus a squared u prime l squared, which is exactly, so c is basically b minus a since this is squared. So it's basically saying that test functions, their L squared norms is exactly controlled by their L squared norm to be derivative. And this Poincaré inequality is used in an application in differential equations. So suppose I have this equation, the double derivative of u minus of this is equal to f of t on a to b, and I have the initial value u of a equals u of b equals 0, where f is a known function, where f is known. We want to solve for u. So classically this is hard hard to do, especially when f is not a nice function. A weak solution is again given by, if I multiply by v here, yeah, so multiply by v of t, where b is a test function, then I can integrate both sides. I'm using integration by parts. This left hand side becomes exactly u prime t v prime t dt from a to b, and the right hand becomes f of t v of t dt a to b. And here we can show that a solution must always exist since, okay, on that the advantage here is that this mapping u to v, which maps it to a to b, u prime v prime. That's exactly what I said. Yeah. So this is actually an inner product since u myself at the endpoints. This defines an inner product on x0 on specifically. So I should write this. And the right hand side, where I map a function v in x01 to the linear or to the integral f v a to b. This is an inner product. And this is a bounded unit function. To show this is an inner product, we require a Poincaré inequality. And so the bounded unit function. So that means v mapping to fb by the Rice representation theorem, there must exist a u satisfying this inner product. That means if I denote this linear by L, that is L is defined to this dt. The Rice representation theorem tells me that there exists a u satisfying this exactly this equation. This is a bounded unit function and this is an inner product. So there exists a u satisfying that the prime must be satisfying this. This is exactly that. And the theorem also tells me that such a u is unique. So we have shown that given any f, we can find a weakly differentiable u which is unique and it always exists. To come to some closing remarks. So closing remarks. So this is what I showed today was also this is HN, but this is a very wide theory. In fact, we define WKB, which is basically all f in p integral function, all p integral functions f with f f prime dot f kth weak derivative all lying NP. This is all the p integral functions whose weak derivative up to the kth order all lying NP. This is defined as WKB. This is also an also a closed linear space, and the norm here is defined as this summation from j equals 0 to k, the NP norm of all the weak derivatives up to kth order, or p 1 by p, and again our theorem says that WKB equipped with this norm is a Banach space. And moreover, the spaces WK2 on AB are exactly the spaces HKA. And for some final closing theorems, from closing theorems, we have this thing. If UV are weakly differentiable, then their product is also weakly differentiable with UV prime as a U prime V plus UV prime. This is the product theorem. And another theorem is the fact that if U is weakly differentiable and I have a continuous differential function C whose derivative is essentially bounded on R, then C composed with U is also weakly differentiable, and this is with the fact that the weak derivative of this evaluates exactly to P prime of U dot U prime. And this is really useful because one can show that. So this result is not really easy, and we can show that if U is in H1, then mod of U is in H1, and the derivative is given exactly as sin of U dot U prime. And moreover, if U is in H1, then U plus, which is defined as this max of 0 and U is also in H1 with weak derivative as this U will be U prime. So this is where I would like to end my talk. So far we showed that Sobolev spaces, their definitions, their completion, and how we can consider Banach and Lebesgue from them. And we showed as a good application where they show that such a solution always exists and is unique. And we also have the product and chain rule on the space. So yeah, that's where I would like to end it here. If anyone has any questions, you can ask them now.
You used right representation theorem for I believe the Sobolev space is infinite dimensional. So you must need some extra assumptions. Because for finite dimensionals,
this extra assumption, the right representation theorem also requires completion and also requires a bounded integral function,
Which is there for any inverse space.
it satisfies
for any neighbor space.
for any space.
For any space or any.
Where you have a bounded integral function, that's all you need.
For any inverse space.
Thank you, Ramdas, for the talk. Anyone having any extra questions? So let's thank our speaker again.